Let's take a closer look now at the definition of a radian measured angle, and we'll see that this particular definition gives us a relationship that's quite important as long as angles that we're using are measured in radians. So let's take a look at what it actually says. Okay, so suppose we have this circle, and let's say that we have an angle and let's give this angle a Greek name. Let's call it that symbol. It's really an oval with a line through it. And let's say that R represents the radius of the circle, and then for whatever reason let's use S out here for the length of the arc. We use the S more in the physics setting to indicate displacement, but it's also common as we're talking about the relationship between the radian, the radius, and the length of the arc. Now, the definition of a radian says that the number of radians tells us how many radii there are out here in this arc. So if, for instance, our radius was equal to 3 and our radian angle was, say, 1, then we know that S here is equal to 1 radius, so our arc would also be 3. If we change theta to, say, 1/2, then our arc out here would only be 1/2 of R. So the length of the arc would be 3/2. So this particular definition, the definition of radian measure, because it tells us the number of radii in the arc, gives us this very nice relationship that is written symbolically in this fashion. Symbolically, we can see the relationship is expressed as S equals R theta. And again, notice that this is a direct symbolic representation of what the definition of a radian measured angle says. It says the length of the arc, S, will contain theta radii. The number of radians, which we're representing with theta, is nothing more than the number of radii contained in the arc, and therefore, if we know the length of the radius and the size of the angle, we can multiply and find not only the length of the arc, but its unit of measure. One of the neat things about the radian measure is that it's not a labeled measurement, it's just a quantity of radii, so that we have a straightforward labeling system as well. Whatever we measure the radius in, the arc is naturally measured in that same way. So let's take a look at a few more examples. Suppose now that we have a particular circle that has a radius of 5 inches and an angle of 4 radians. Now again, it's very important that the angle be measured in radians because this is only valid for that particular unit of measure. That means if the angle that we have is in degrees, we're going to have to figure out how to convert the number of degrees into a quantity of radians. But for now, we've got this angle, theta equals 4, and a radius of 5, so we can figure out what the length of S is. If we replace the r with 5 inches and theta with 4 and multiply, we find that the length of the arc is 20 inches. And again, notice since the radian is not per se a label as inches are or feet or that kind of thing, it's just a quantity of radii. It has no effect really on the fact that the arc is going to have the same label as the radius. So let's take a look at another example. In this example, notice that we know the length of the arc, and again we have an angle that's 4 radians, and we want to find r. So we need to plug in the 6 4s, and we need to plug in the 4 for theta and solve. And here we have the solution. Again, notice that even though it's not written in there, the 6 is in inches, and we're going to divide by 4 radii. So we're taking 6 inches, dividing it into 4 equal pieces to find the length of the radius, which again has to be measured in the same units as S, because there's nothing to cancel out that inches if you look at that inches as an algebraic factor. So we have actually just shown here that this formula can actually be rewritten as r equals arc length over the angle theta, which we all know from past algebraic experience that you can take a formula and rearrange it as long as you use the correct rules of equality and algebra. One more example. In this example, we know the length of the arc, we know the radius of the circle, which means we can find the size of the angle. And that means, to begin with, we could just rewrite the original formula so that it's solved for theta, or we could plug in and solve it like we would any other equation. Somehow it seems more aesthetically pleasing to me to go ahead and solve the formula for theta first, so that we again can see that if we divide both sides of the original equation by r, we have a formula that will give us the angle theta in radians and only in radians. So now plugging in, we find that theta is going to be 4 inches divided by 2 inches. We treat the inches here just like we would any other algebraic factor, and notice that they cancel. So in other words, we kind of treat it like it's 4 times inches and 2 times inches, so that by using algebra with the labels as well as with the other numbers, we are able to manipulate labels to have them come out, to have the algebra actually show us what the label should be. So in this case, the inches cancel. We get 4 divided by 2, which is 2. 2 what? Well, since this is an angle, that 2, it is telling us purely the number of radii of 2 inches in length that are contained in that arc that's 4 inches in length. We have 2 radii. So again, it's saying that this angle measured in radians is really just a quantity in its pure sense. It's not 2 of any type of measurement. It's just a quantity of radii, and that's where its name comes from as well. So understanding the definition of the radian as a unit of measure for angles gives us this unique little relationship that is only true for angles that are measured in radians. And we need to not so much memorize that definition as we need to learn it and understand it and be able to use it.